So, hello everyone again. This is lecture 2 part 3 of alternating current. In the previous part of this lecture only we have started with the discussion regarding AC voltage applied to a capacitor. Let us move on with the further discussions. Only introduction was being done regarding what happens when only a single capacitor is being installed in a DC circuit. Let us further our discussion regarding what happens now when a capacitor is being installed in the form of AC in a AC circuit. Okay. So, we will try to understand what happens with the current, what is the value of current being obtained, what is the value of instantaneous power, what is the value of average power over a one complete cycle and so on. So, that thing being said, this is lecture number 2 part 3 of alternating current. I am Sameer Lavankar. Let us begin our discussion. So, currently we are on this fifth topic, that is AC voltage applied to a capacitor. After this is being done, we will move on to AC voltage applied to a series LCR circuit. Okay. So, introduction is being done, AC voltage applied to a resistor is being done, representation of AC current and voltage by rotating vectors is being done, AC voltage applied to an inductor is done, and now let us try to understand AC voltage applied to a capacitor. Okay. Fine. So, AC voltage, so these all things are already been explained in the last class only. So, basically what happens in a AC voltage supply, there is no case scenario in which no current is passed through the circuit, it either limits or regulates the current. Okay. But why is this case scenario in AC circuit? It is the case scenario because the capacitor is alternately charged and discharged. Why it happens? Because the current reverses each half of the cycle. Okay. So, in one case scenario it goes like this, in another case scenario it goes like this, and that is why there is difference in the amount of charges being stored in the plates. Okay. Fine. So, now let us try to understand, let us try to derive the similar case scenarios of current as in we did for the AC voltage applied to a resistor and inductor. So, here let Q be the charge on the capacitor at any time t. Now, the instantaneous voltage V across the capacitor will be what? So, we have understood this in the chapter of electrical charges, that this value of voltage is nothing but equal to small q divided by capital C, right. So, simple formula. Now, let us try to apply Kirchhoff's loop rule here. So, from, let me write, from Kirchhoff's loop rule, we will get that value of voltage V is nothing but equal to small q by C. This voltage V is nothing but equal to Vm sin omega t is nothing but equal to q by C, correct. Now, what is the basic agenda for doing this all calculations? We need to calculate the value of current. As nothing is given directly in function of current, what we can write? We can write as what is I is nothing but equal to dq by dt. We know that current is defined as the rate of change of charges passing through a circuit per unit time. So, rate already happens in time only. So, it is nothing but rate of or change in amount of charges passing from point A to point B in some time t. So, in differential form we can write this current as nothing but equal to dq by dt. So, if it is equal to dq by dt, so we can just write, so from this equation what we get? We got that small q is nothing but equal to Vm capital C sin omega t, correct. So, we can write this as nothing but equal to d by dt of Vm capital C sin omega t. This is nothing but equal to Vm capital C omega cos omega t, correct. So, basically what we got? We got that small I is nothing but equal to Vm C omega cos omega t, or in another case scenario we can write this equation as Vm upon 1 by omega c. Okay. So, these are both are same only into cos omega t. So, this is the first equation of current which is being derived. We can do the same thing which we did for inductor part also, that is in the case of cos omega t we can write. So, previous case scenario we got minus cos omega t, because we got cos omega t here we can write this cos omega t is nothing but equal to sin of omega t plus pi by 2. Please remember this trigonometric equation very clearly. minus cos omega t is equal to sin omega t minus pi by 2, but cos omega t is equal to sin omega t plus pi by 2. And because this is the case scenario here, I can again write this equation of current as nothing but equal to V m upon 1 upon omega c into sin of omega t plus pi by 2. So, this is the final equation which we obtained for the current when the voltage passing through the circuit is V m sin omega t. Okay. So, let us now derive all these things. So, that thing being said, what we got, let me write the equation again. So, it is as not derive as in now define the concept which we just derived. So, we got that what is I is nothing but equal to I m sin of omega t plus pi by 2. What is I m here? I m is again nothing but amplitude of current, which is nothing but equal to V, which is nothing but equal to V m upon 1 by omega c. So, in the case of inductor we got this value as equal to omega L, in the case of capacitor we are getting this value as 1 upon omega c. Similar concepts again, this 1 upon omega c is nothing but analogous to reactance, and that is why now 1 upon omega c is basically called as capacitive reactance, and it is denoted by X c. Okay, it is called as capacitive reactance and it is denoted by X c. Okay. So, therefore, what we can write? We can write basically that amplitude of current I m is nothing but equal to V m by X c. Please remember clearly, omega c is not X c, 1 upon omega c is X c. Okay. People try to confuse sometimes that you need a value which is a little not sort of direct assumptions or direct equation. So, please remember X c is not omega c and X c is 1 upon omega c. Why is that case scenario? Because we are trying to define or denote a equation or a number by something which is analogous to resistor, right. Omega c is not a resistor, omega c has a unit of 1 upon ohms. 1 upon omega c is having a unit of ohms, and that is why X c is equal to 1 upon omega c. So, let us say in some exam, if the question comes that X c is proportional to omega or X c is inversely proportional to omega. So, the answer should be X c should be inversely proportional to omega. The reason is that because X c is not defined as omega c, it is defined as 1 upon omega c. Okay. So, that was just simple explanation. So, that thing being said, I think that was all required. Yes. So, now let us try to understand same things which we understood for inductor. So, the dimensions of capacitive reactance is the same as that of resistance and its SI unit is ohms, similar to inductor. So, it only for inductor it was omega L, for capacitor it is 1 upon omega c. Okay. The capacitive reactance limits the amplitude of the current in a purely capacitive circuit in the same way as the resistance limits the current in a purely resistive circuit, similar to the inductor concept, but it is inversely proportional to the frequency of the capacitance. Okay. So, as X c, please remember X c, S c denotes here capacitor. Okay. So, X c is equal to 1 upon omega c. It is quite clear that X c is inversely proportional to omega, and similarly X c is inversely proportional to c also. Okay. So, it is inversely proportional to frequency and the capacitance. Next, a comparison of the equation. Next is a comparison of the equation show that the current is pi by 2 ahead of voltage. Okay. So, as V is equal to V m sin omega t, and the current which we got was nothing but equal to I m sin of omega t plus pi by 2. That is why you can see clearly that if we are drawing the value of voltage here, we are trying to draw the value of current phasor in front of it, okay, because this time the current is pi by 2 ahead of voltage. In the case of inductor, it was behind, or it was lagging behind the voltage, and that is why current is forward this time and voltage is behind this time. Again trying to draw the diagram for your waveforms. So, just draw horizontal lines from here, draw horizontal lines from here, you will get the value of voltage at that point at the time t1, and similarly for the value of I, what we will do, again draw horizontal line, draw horizontal line, you will get the value of current at the time t1. Okay. Fine. So, that thing is also being done. Then figure A shows a phasor diagram at instant t1. I explained what is being happening here, why it is said that why why current I is drawn in front of capital V, because the diagram is in anti-clockwise sequence. Here the current phasor I is pi by 2 ahead of the voltage phasor V, as they are rotated counterclockwise. Okay. Next thing is figure B shows the variation of voltage and current with time t. So, you can see that the variation of voltage and current with time t is being explained there. And so, we see that the current reaches its maximum value earlier than the voltage of 1/4 of the period, right. So, as you can see that if I try to explain, okay. So, this was the peak value of current and this is the peak value of voltage. You can see clearly that the current observed its maximum value before voltage, okay. Voltage observed it after, at some after forward time, but current observed it before only. So, what we can say that current is ahead of voltage, by how much time? By how much time? The time is equal to phasor diagram, that is pi by 2, or we can say that 1/4 of the period, current observed its peak 1/4 of the period before this voltage. So, I think this is also being done. Now, let us try to solve for instantaneous power now. So, time to नहीं हुआ ना. So, let us try to solve for instantaneous power now. So, Pc is nothing but equal to I into V. So, it is nothing but equal to I m into cos of omega t into Vm sin of omega t. The difference in instantaneous power for a capacitor and an inductor is only this, that for the case of inductor it was minus Im cos omega t into Vm sin omega t, but in the case of capacitor it is Im cos omega t into Vm sin omega t, only a difference of plus and minus being observed here. So, similar case we can write this as nothing but equal to Im Vm cos omega t sin omega t, multiplying and dividing it by 2, we will get it is nothing but Im Vm by 2 into sin of 2 omega t. Okay. This is the instantaneous power Pc. In the similar case scenario, we can write the average power also. So, average power over one complete cycle is, how we write this? Let me write it as capital Pc. It is denoted in this case scenario, it is nothing but equal to Im Vm by 2 into sin of 2 omega t. As all other things are constant, we can remove this out of this brackets, and hence we will get it as equal to sin 2 omega t. We know that sin n omega t or sin cos n omega t in a complete cycle is always 0, and therefore, we got the value of average power as nothing but equal to 0, right. So, thus we see that in the case of an inductor the current lags the voltage by pi by 2, but in the case of capacitor the current leads the voltage by pi by 2. Okay. So, those were all the concepts I guess for capacitor. Let us try to solve one, I think 2-3 examples are there. Yes, try to solve as much as possible and then we can move on to the next concept. Okay. So, let us look at the first example here. The example states that a lamp is connected in series with a capacitor. Predict your observations for DC and AC connections. What happens in each case if the capacitor is reduced? Okay. So, simple question is given, quite evident what will happen at a DC source, there will be a no change if the C is reduced or increased, because it is a direct current. When the plates are being charged completely, there is no current in the circuit. But what happens in the case of inductor, sorry, what happens in the case of AC source, because of regulating voltage, because of a waveform of the AC source, what will happen, there may be a change or a change in the what we can say, there may be a change in the lamp shining brightly or reduced, because we can change with the value of C. How we can change with the value of C? Because the reactance is nothing but 1 upon omega C. So, if C is reduced, omega 1 upon omega C will increase. If C is increased, 1 upon omega C will decrease, and therefore we can regulate the value of reactance. Okay. So, everything which I just said is being written here. So, when a DC source is connected to a capacitor, the capacitor gets charged, and after charging no current flows in the circuit. Quite evident, this was also been explained in the introduction part of this capacitor concept, and therefore, after the complete charging of capacitor is done, the lamp will not glow. Once current is 0, there will be no change even if C is reduced. So, even if you try to reduce the C or if you try to increase the C, there is no change happening. Why? Because DC current is being observed here. Once the capacitor is charged, there is no way we can try to take the charge out of it, and hence the lamp will not glow. Why will lamp not glow? Because after charging, as the voltage keeps on increasing, there comes a time when it is completely charged, there is no current passing through the circuit. What happens in the case of AC circuit or AC source? The capacitor offers capacitive reactance, that is 1 upon omega C, and the current flows in the circuit. So, therefore, the lamp will shine. What will happen when the C is reduced? So, if C is reduced, as you can see here, the capacitive reactance will increase, correct. So, reducing C will increase reactance and the lamp will shine less brightly than before. You can see it logically also. If I try to react, or if I try to give more resistance, what will happen? If more resistors are provided, then the amount of voltage difference across the lamp will reduce, and that is why the amount of brightness will also reduce, correct. But if amount of resistor is reduced, or apart from lamp, then the amount of voltage which is being supplied to the lamp will increase, and then it will shine brightly. Okay. So, going with that concept here, as value of C is increased, reactance is decreased, because question I have reduced. Okay. So, if C is decreased, then the reactance is increased, or the amount of resistance being offered is increased, and therefore lamp will shine less brightly, okay, or lamp will become dim. Okay. So, that was a logical question here, and that is being explained. Moving on to the next question. So, a 15 microfarad capacitor is connected to a 220 volt 50 hertz source. So, basically capital C is given to you, capital V is given to you, and nu value is given to you. Find the capacitive reactance and the current in the circuit. If the frequency is doubled, what happens to the capacitive reactance of the circuit, okay, and the current. Okay. So, first of all, let us calculate the value of capacitive reactance. What is the value of capacitive reactance? It is nothing but equal to 1 upon omega C. What is the value of capital C? Capital C is given to you in the question. What is the value of omega? Omega is nothing but equal to 2 pi into nu. Nu is given to you as 50 hertz, correct. So, just try to write everything, you will get the value of XC as nothing but equal to 212 ohms. First question is done. Second question is nothing but to calculate the value of current. How to calculate the value of current? I already told. Whenever RMS current is asked, do nothing, just write capital I is nothing but equal to capital V by X. So, in this case scenario it will be XC. Okay. So, it is 220 divided by XC, XC is nothing but 212, and therefore, you will get the answer as 1.04 amperes. This is, please remember, this is the RMS current. But because the value of peak current is also being asked, what you will do? We know that peak current is nothing but a little higher than this RMS current. So, we will write it as nothing but root 2 into I, correct. So, it is nothing but 1.41 into 1.04, and therefore, you will obtain the value of peak current as nothing but equal to 1.47 ampere. So, that is the peak of the amplitude of the current being observed in a wavy form or in the wave form. So, that thing is also explained. Next thing is, so this current oscillates between plus 1.47 amperes and minus 1.47 amperes, and is ahead of the voltage by pi by 2. Why it is ahead? Because it is a case of a capacitor. Okay. Next question is, if the frequency is doubled, what happens to the capacitive reactance and the current? Okay. So, if the XC, so basically if omega becomes 2 omega, XC becomes 1 upon 2 omega C, correct. That means the value of capacitive reactance is divided by 2. If capacitive reactance is divided by 2, what will happen to the current? So, basically if XC is reduced, by 2, that means current is doubled. Okay. So, that thing is only been explained here. So, how to explain it mathematically? It is nothing but V upon x c by 2. So, therefore, we can write it as nothing but 2 into V by x c or I dash. So, it is nothing but 2 into I. So, current is doubled and the value of x c is or x c dash is nothing but equal to x c by 2. Okay. So, this was the mathematical explanation. Let me stop it here only. In the next class, I will explain this last question and then we can move on to the new concept, that is AC voltage applied to a series LCR circuit. So, just the course progress for you. We have completed with the introduction, AC voltage applied to a resistor, representation of AC current and voltage by rotating vectors, AC voltage applied to an inductor, and currently we are on the 5th topic, that is AC voltage applied to a capacitor. Only one example is remaining and then we can move on to the next concept, that is AC voltage applied to a series LCR circuit. Okay. So, that thing being said, let me stop the discussion here only. Thank you so much.